And welcome back to 5.1 Notes, where we're taking a look at how these electrons behave around the nucleus. In the last podcast, we took a look at the Bohr model of the atom. What Niels Bohr said was that electrons travel around the nucleus like planets around the sun. They moved in fixed pathways at certain distances, and those are the only distances that the electrons can travel. In fact, I'm just going to change my color up just here for a second. The electron is not allowed to be at, say, that particular distance or at this particular distance. That's not allowed. The electron, according to Niels Bohr, must be in certain distances, traveling in certain pathways, and that would explain the line spectra of hydrogen. Scrolling back up here just for a second, what he said was that when the electron makes jumps or is excited to outer energy levels, let's just say that the electron was here at n equals 2, and it's given energy to be pushed all the way out to the outer energy level. It's in an excited state. As that electron returns back to its ground state, it's going to give off a certain fixed amount of energy. And that certain fixed amount of energy could correspond to a wavelength of visible light. All right? And this model, once again, was very important because it was the first quantized model of the atom, meaning it was the first one that incorporated the idea that energy can only be absorbed and emitted in fixed quantities. Now, the problem is, scrolling down onto the next page, the problem is that this model only worked for hydrogen, where you have only one electron. Scientists were unable to describe the moving. Let me just pause just for a second. What they did, because let's just say that this is the nucleus, if the Bohr model of the atom had these circular orbits, all right, they tried all sorts of things. This shift the orbits off-centered. This make them elliptical maybe instead of circular. This changed the distances between the individual orbits. They tried everything. But the problem was, once you introduce a second, third, fourth, and many more electrons, the electrons start to repel one another. So the idea of the electron moving in a fixed pathway may actually work for hydrogen because it's not being repelled by anything else. But as soon as there's anything else there that's repelling it, inside the atom, now we have problems. And so scientists were unable to describe the electron moving as a particle around the nucleus. So now they're stumped. What do you do? Since we can't make this particle model work, they started looking for other models. Well, here's the deal. If light can be described as both a wave and a particle, and it was done so by Albert Einstein, can the electrons? And the answer is yes, it can. A guy by the name of Louis de Broglie, in fact, showed that electrons can be described as a standing wave, or showed its wave properties back in 1924. Now, we describe them as standing waves. I'm going to put that in parentheses here. And that analogy is more like a guitar string. Okay. Now, a guitar string, when you pluck it, will give a particular sound. But that sound depends on a lot of different items that the guitar string has. For example, it's what it's made up of, how thick the guitar string is, how tightly it's strung on the guitar, whether or not you're pushing down on that particular string on the frets on the neck of the guitar, how you pluck the string, etc. There are a lot of different characteristics to that guitar string, and it gives rise to lots of different properties. The electron is the same way. Except we're not talking about sound properties, we're talking about chemical properties. We're talking about the energy that the electron has. We're talking about the position it has around the nucleus, how it's traveling around the nucleus, how easily that electron is removed from the nucleus, etc. All of those properties can be described using its wave properties. However, we are running into another problem. The problem is, once they started calculating some of the different properties using its wave functions, came what's called the uncertainty principle. Werner Heisenberg discovered this uncertainty principle, and what he found was that it's impossible to know both the position of the electron and the momentum of the electron or the particle at the same time. Here's the problem. if we're looking, and I'm going to draw a picture of an eye here. Here's the eye. Okay, if we are looking at a person moving, okay, here's a person, or any object that's moving. How do we see that person moving? Let's just say the person is moving in this direction. Well, photons of light will strike the person, and it's going to move back to our eye, and we're going to see the person at a particular position. If the person is moving closer, this is the same person now, then the next round of photons will reach our eye a little bit sooner, and then a little bit sooner, and so on and so forth. So we can tell that objects are moving because the photons of light are reaching our eyes a little bit quicker than they were just a split second ago. Now, when you try to do the same thing with an electron, here's our eye, and here's the electron. Let's say that the electron is traveling in this particular direction. Let's say the electron is moving towards us. When a photon of light strikes the electron, the particle of light might reach back to our eye. Not a problem. However, the electron is no longer traveling on that same pathway. The electron is so small that when a photon of light strikes it, it actually moves in a different direction. We don't know what that direction that is. It bounces off the photon of light like billiard balls on a pool table. And so we can never know exactly where that electron is in the next split second. You only know where it was. Now, that doesn't work that way with people because photons of light don't move our position. And technically speaking, there is a little bit of uncertainty about where each individual person is at any given point. However, that range of error is so small that we would never detect it. However, when you're dealing with the size of the electron and the size of the error where it could be in the nucleus, all of a sudden it becomes a very big deal. All right. So the bottom line is we cannot know exactly where the electron is and where it's going at the exact same time. So, because of that, Austrian physicists devised a way that we could describe the behavior of an electron, which became known as the wave mechanical model of the atom. Some people call this the quantum mechanical model. And some people even call this the electron cloud model. And you'll see why in just a second. But here's the deal. This model excuse me, this model determines the allowed energies. The allowed energies an electron can have, and the likelihood check the spelling on that the likelihood of finding it in various locations around the nucleus. Okay, we know the distances that the electron can be at, but we don't know exactly where it's going to be at any given point. So, in the next podcast, we're going to describe this idea in what's known as the Firefly experiment.